Let's look at a surface integral of a vector field. In physics and engineering, when you compute the surface integral of a vector field, that's called flux. And that's one of the reasons that usually the scientists and engineers will require the outward unit normal. Now, just like with the line integrals, when we compute the line integral of a vector field, the norm component absorbs. And so even though you start with a unit normal, that normalizing component absorbs. So once you compute a normal, you can use that in your calculation. So just remember from the definition that the norm factor absorbs and you don't see it in the calculation, just like we saw with the line integrals of vector fields. So don't be bothered by that. Just realize that everything is taken care of. Now, the surface here is z equal 1 minus x squared minus y squared, and z is greater than or equal to 0. And so again, we will parameterize using the Cartesian coordinates. So we'll have an x, a y, and a 1 minus x squared minus y squared. Now again, we have a nice convenient formula for the normal. The Rx cross Ry is the negative of Zx, negative Zy, comma 1, and that's easily seen to be 2x, 2y, and a 1, and that's the outward normal that we would need. Now, in this particular case, what we're doing is computing the surface integral of a vector field, and our vector field is right here. I've highlighted it in red. It's the vector field x, y, z. And so the notation looks similar to what we had before. Now, you can think of the ds as a vector, which would incorporate the outward normal, or you can write it in this particular notation. Either is fine. Physicists and engineers will vary, but this is certainly acceptable. And so now what we have, if we project this into the xy plane, we certainly have x squared plus y squared is less than or equal to 1, and we have x, y, z dotted with the normal 2x, 2y, comma 1. So again, just like the line integral as we had before, we perform the dot product and we get the double integral over x squared plus y squared less than or equal to 1 of 2x squared plus 2y squared plus z. And of course, we need to replace z with this xy equivalent. And so that will give us the double integral over x squared plus y squared less than or equal to 1 of 2x squared plus 2y squared plus 1 minus x squared minus y squared. And now just combine terms, and we're left with an x squared plus y squared plus 1. And again, with all the circular symmetry, we might as well convert to polar coordinates. So of course, the x squared plus y squared is replaced with r squared, and the area element dx dy is replaced with r dr d theta. And so again, a very straightforward computation with polar coordinates. So now what we can do is multiply through by the r. So we have the double integral from 0 to 2 pi and then 0 to 1 of r cubed plus r. Very simple. Add 1, divide by the new power. We'll get r to the 4th divided by 4 plus r squared divided by 2, evaluated from 0 to 1. Of course, the lower limit zeroing out the antiderivative, and that leaves us with a 1/4 plus a 1/2, which I just wrote as a 2/4, so we can easily combine those. So basically, we're taking the integral, theta integral of a constant. So we get 3/4 theta evaluated from 0 to 2 pi, and of course that'll give us 3/4 times 2 pi, and of course the 2 absorbs into the 4, and we get 3 pi over 2. So it seems like we've been doing some unit circle trigonometry. But again, just remember the differences between the surface integral of the scalar function and the surface integral of the vector field, just like the counterparts that you have with line integrals. And we are done.